and Christoph for quickly agreeing to give these two talks. So it's a pleasure to have Zakhar Kabluchko and Christoph Thäle. So they'll be speaking on spherical stochastic geometry. So as Zakhar will give the first talk and then Christoph will give the second one. So for asking questions and so on, I'd request the participants to post the question on chat, and then hope probably Christoph would answer them. And if necessary, we might interrupt Zakhar and ask the question. And then at the end of the talk, you can raise your hand. There is an option of raising hand on the in the Zoom, and you can raise your hand, and then I will unmute the participant and they can ask the question. Okay. So yes, Zakhar, over to you.
Yes, so thank you very much for the invitation. The goal of the aim of my part of the talk is to define the conic intrinsic volumes of convex cones, or which is almost the same, the spherical intrinsic volumes of spherically convex sets. So let us start with some definitions. Rn denotes, as always, the Euclidean space of dimension n, and then we define a hyperplane. So a hyperplane is, so I denote it by HU, and U is a vector in the unit sphere. And a hyperplane generated by U is just the set of all x in Rn, such that the scalar product of x and U is 0. So a hyperplane is just a set of solutions to a homogeneous linear equality, and such a hyperplane passes through 0 in this definition. Now, what is a half space? A half space, denoted by HU minus, associated with some vector U in the unit sphere, is the same but with an inequality. So the scalar product of x and U is, say, smaller than 0. And of course, one can also define HU plus in a similar way. And this is a half space whose boundary passes through the origin. Now a cone is just an intersection of a finitely many half spaces. So C is an intersection of finitely many half spaces HUI minus. Actually, this should be called a polyhedral cone, because a convex cone in a general definition is an intersection of infinitely many subspaces, of an arbitrary number of half spaces. We consider here only polyhedral cones, so they are polyhedral. And here U1 and so on, UM are unit vectors in the space. So a polyhedral cone can be defined as a set of solutions to a finite system of homogeneous linear inequalities. And finally, a spherically convex set is just an intersection of a convex cone with the unit sphere. So it is C intersected with the unit sphere. And it is clear that there is a one-to-one correspondence between cones and spherically convex sets, or it would be better to say spherical polytope, because the cone is polyhedral. And there is a one-to-one correspondence between them, and it is sometimes convenient to consider cones and sometimes convenient to consider spherically convex sets. Now there is an equivalent definition of the cone. Of a cone, namely a polyhedral cone can be defined as a positive half of finitely many vectors, V1, Vk, where a positive half is just the set of all positive combinations of these vectors, I from 1 to k, and all lambda I are non-negative. So we can define a cone either as an intersection of half spaces, say something like that, or we can define it as a positive half of finitely many vectors. Say, in the simplest case, it would be such an angle. It's an example of a cone. Now, what are examples of cones? There are, first of all, some trivial examples like linear spaces. I'm sorry, I cannot. Okay, so like linear spaces or like a half space, something like that. Maybe a less trivial example a Weyl chamber, or there are many Weyl chambers. Here we consider Weyl chambers of type A. It is defined as a convex cone VAN, and it is given by the following set of inequalities: x1 is greater or equal than x2, and so on. And this is greater or equal than xn, where x1, xn are the coordinates in Rn. So it's just the set of all points in Rn which are given by whose coordinates are monotone decreasing. And the Weyl chamber of type B is very similar. It is a set of points whose coordinates are decreasing and greater than 0. And evidently, both Weyl chambers are sets of solutions to a finite system of linear inequalities. So they are really positive, they are really polyhedral cones. And one more example, the positive orthant. It is the set Rn plus of points with non-negative coordinates. So xi is greater than 0 for all I. In dimension 2, it is something like that. It is a quarter plane, and it's evidently a convex cone. Now I'm going to define the intrinsic volumes of cones. And to this end, I need first to define the notion of projection. So let C be a cone. I consider only polyhedral cones from now on. Then the projection on C is defined as follows. It is a map which assigns to every point from Rn the point from C which has the smallest distance to this point. So the best approximation of this point which belongs to C. So PC of x, where x is any point in Rn, is the minimizer of the distance x minus y over all y in C. And it is known that for every convex set C, the minimizer exists uniquely. And for example, if x is in C already, then PC of x is of course x, because then the minimal distance is 0. Now let us draw a picture. So assume this is a cone in dimension 2, this is C, and if x is in C, then it is mapped to itself by this projection. So all points inside of C are mapped to themselves. Now, what happens to points outside of C? First of all, there are points which are mapped to this side. So they are mapped like this. This is the best approximation. And there are points which are mapped to the other side, mapped like this. But also there are points which are mapped to the origin, so for which the best approximation is the origin. These are all points which are here. So they are mapped to the origin. And we see that this projection mapping maps any point either to or to some face of C. And with this knowledge, we can define the conic intrinsic volumes. So the conic intrinsic volumes of C are defined as follows. Vk, the kth conic intrinsic volume of a cone C, is defined as the probability that a point U, which is uniformly distributed on the unit sphere. So U is uniformly distributed on the unit sphere. So I take a point which is uniformly distributed on the unit sphere, I project it to the cone, and then I ask for the probability that this point is in some k-dimensional face of the cone, or more precisely, that it is in the relative interior. It is in the relative interior of some, yeah, probably I have to remove that, k-dimensional face of C. and U is uniform on the unit sphere. So what does it mean, relative interior? Well, okay, for example, if I have a point which is, say, here, this one, then it is mapped to the origin, and the origin is, for example, is contained in the one-dimensional phase and in this one, the other one-dimensional phase, but it is not in the relative interior. Relative interior of a phase is the set of points which are in this phase, but not in a phase of a smaller dimension. So, for example, the origin is not in the relative interior of these one-dimensional phases. It is outside, it is on the boundary. So, for example, all points which are here are projected to a relative interior of a one-dimensional phase, and all points which are here are also projected to a relative interior of a one-dimensional phase, and all points which are inside are projected to a relative interior of a two-dimensional phase. So they contribute to one-dimensional and two-dimensional conic intrinsic volumes in this sense. Now this is defined for every k for which we have phases of dimension k, namely for 0 up to n. So there are n conic intrinsic volumes, and actually one more remark, this U, which is uniform on the sphere, can be taken to have any distribution which is spherically invariant. So for example, the standard Gaussian distribution would also do, because the probability would not change, as one easily sees. It is the same, as long as the distribution is spherically symmetric. Now there is an evident property of these conic intrinsic volumes, which is not present in the usual convex geometry. So we are now in the conic convex geometry in some sense. It is clear that, first of all, the sum of all these volumes over all k is equal to 1, simply because any point has to be projected to some phase. It has to be projected either to a two-dimensional phase, or to a one-dimensional phase, or to a zero-dimensional phase, in this example. And in general, it is projected to phase of some dimension, so the sum should be 1. And second, all these intrinsic volumes are non-negative, so they form a probability distribution. Now let us look maybe at some simple examples. So example 1, let's see be a j-dimensional linear subspace. So it is a linear subspace of dimension j. So what are the conic intrinsic volumes? Nu k of Lj is equal to, well, we have a subspace of dimension j, and now what is the projection? What is the projection? It's just the usual orthogonal projection, and under this projection, every point is mapped to a j-dimensional phase. So this probability is 1 if k is equal to j, and it is 0 if k it is not equal to j. So it's just a delta distribution in the case of a linear subspace. Now let's consider something more involved, the orthant. C is the positive orthant. How to compute this probability? Well, let us take, instead of U, a standard Gaussian vector, which is also spherical symmetric. So let psi1, psi_n be standard Gaussian on Rn. And then we try to project this vector. So what is the projection PC of psi1, psi_n to the positive orthant? So here is the positive orthant, and now I have some point, I want to project it. So I want to approximate it by a point with positive or non-negative coordinates in the usual Euclidean metric. And how to do that? Well, if all psi i's are positive, then there is nothing to approximate, right? Then the approximation is the point itself. But if some coordinate is negative, then the best approximation to this coordinate is just by 0. So I have to approximate this coordinate by 0 if it is negative, which means that this projection is just the vector with coordinates psi I if psi I is positive, and 0 if psi I is negative. I from 1 to n. So just all negative coordinates are just replaced by zeros. And this is the approximation. And now in order to determine the conic intrinsic volume, we have to compute the probability that this projection is in a k-dimensional phase, or is in the relative interior of a k-dimensional phase of the orthant. Now, what are the k-dimensional phases of the orthant? So first of all, the orthant is given by the inequalities x1, xn are all greater than 0. This is the orthant itself. And now, what are the k-dimensional phases of it? Well, in order to construct phases, we have to replace some inequalities here in the definition of the cone by equalities. And how many inequalities should be replaced by equalities? Well, the number should be such that the phase is k-dimensional. So the number of remaining inequalities should be k. So we should have k variables which are greater than 0, xi1 greater than 0, xik greater than 0, and all other coordinates are required to be 0. And in this way, we obtain a k-dimensional phase, right? So all of them are of this form. And now, what is the probability that some point is projected to such a k-dimensional phase? Well, it is the probability that k coordinates of this point are non-negative. Exactly, k coordinates are non-negative, and all the others are negative. Then they are projected to 0, and then the result is in this phase. So it is just the probability that among these n variables, exactly k are non-negative, or maybe strictly positive. Maybe I'm not very exact here. So k coordinates are strictly positive, but what we have here are just n Bernoulli experiments with probability, success probability 1/2. A success is if we have a positive coordinate, so we want to have k successes in n experiments. So this is 1/2⁴n over k, just because of this binomial interpretation. And we see that the intrinsic volumes of the orthant form some very simple distribution, the binomial distribution with parameter 1/2, or with parameters n and 1/2. Well, okay, actually, my dream would be in this talk to compute the intrinsic volumes of the Weyl chambers, of these two Weyl chambers, which are much more interesting, but I don't think I will manage it in 45 minutes. Or maybe, let's see. Now, let me switch a page. So this is a new page. And maybe one more definition in this. Well, maybe we don't need it. Let me forget about this definition and do the next thing, the Grassmann angles. So let us define the Grassmann angles of a cone C. They are defined as follows: gamma k of C, and k is here again 0 and so on n. So there are n plus 1 Grassmann angles. It is the probability that the cone C is non-trivially intersected by a random n-k-dimensional subspace. Let us denote this subspace Wn minus k, and the probability that this intersection is non-trivial, so that it is non-zero, is the Grassmann angle. Note that every cone contains 0 by definition. So the intersection is always at least 0, but it may be non-trivial. And here in this definition, Wn minus k is n minus k dimensional linear subspace in Rn, and it is random and distributed according to a uniform distribution on all such subspaces. So uniform. So if somebody doesn't know what does it mean, maybe I can define it later in the talk during the talk by Christoph. Now, one special case. Example. If k is equal to n minus 1, then we have here W1. It is one-dimensional linear subspace. So it is a line, a random line with a direction which is uniform on the sphere. in sums. So gamma n minus 1 of C is the probability that such a random line intersects C non-trivially. So I have a cone and I have a random line, and a random line passing through the origin. Here the origin, and we want to have the probability that it is intersected non-trivially. So in this example, what is this probability? I don't know whether you can answer questions, so I will answer them by myself. I'm not sure. I think all are muted, so I will answer it by myself. It is the angle of the cone, right? But not exactly the angle. Namely, if I would take a random direction, so a random direction, not a random line, but a random ray, then the probability that this ray is in the cone is the angle. But if I have a line, then the line can, so for every line we can choose a direction, right? And even if this direction will be here, pointing in this here, it will be okay. The line will still intersect the cone. So this is not the angle, it is 2 times the angle of the cone. It is 2 times the angle of the cone. Alpha of C is the solid angle of the cone. I will define it immediately in a moment. And this is true if, first of all, if the dimension of C is n. And there is one exception: C should not be equal to Rn. Because if C is equal to Rn, then the reasoning with this 2 is wrong. Then it doesn't work anymore. And what is alpha of C? Alpha of C is the angle of the cone, and it is just the probability that a uniformly distributed random variable is in this cone. So uniformly distributed random variable on the sphere in Rn is in this cone. Well, in this definition, maybe it's sometimes more convenient to do the following. Suppose you have a cone in a 3-dimensional space, which is itself 2-dimensional. So the cone is a 2-dimensional angle in a 3-dimensional space. Then with this definition, the solid angle would be 0. And maybe it's not convenient. So I will say here, U is uniformly distributed on the unit sphere intersected with the linear subspace generated by by C. So if we have a 2-dimensional cone in a 3-dimensional space, then this linear space is a 2-dimensional plane. Then we take a uniform direction in this plane, right? And then this is non-zero. Okay, now the main tool which I will use in the rest of the talk is the following Crofton formula. So the following conic Crofton formula. The conic Crofton formula, it says that the Cave-Grassmann angle, so the probability that a linear subspace intersects C non-trivially, can be expressed through the intrinsic volumes. It is 2 times mu k plus 1 of C plus mu k plus 3 of C, and then plus all odd numbers here. So the sum is over all odd numbers. And this is true if C is not linear subspace. Now this sum is infinite, but at some point we have here something which has index larger than n, and then we define it to be 0 by definition. So all terms which have indices greater than 0 are defined to be 0. And now let me give, so I will not prove it, unfortunately, in 45 minutes it's not possible, but I will try to give some applications of this formula to probabilistic questions. And the first probabilistic question is a result by Wendell from the year 1962. Suppose that Z1, Zn are IID points which are uniformly distributed on the unit sphere in the d-dimensional space. So d-dimensional vectors on the unit sphere, and the number n is bigger than d or equal. And now there are 2 possibilities. So for example, if we are in the plane, here is the circle, and we choose here some points randomly. there are two possibilities. The first possibility is that there is a half space which separates these points. So there is a half space containing all these points. This is the first possibility. And the second possibility is that there is no such half space. And this happens if and only if the convex hull of these points contains 0 in its interior. So here is the convex hull, the polytope generated by these points, and if it contains 0, then there cannot be such a subspace. And conversely, if there is such a subspace, then clearly the convex hull is located in a half space and it can contain 0. And the question which Wendell answered was to compute the probabilities of these two events. So let us define P to be the probability that there is a half space containing half space with a boundary passing through the origin, containing these points, and Q is the probability that the convex hull of these points contains 0 in its interior, or maybe I don't want to study these boundary cases because they have probability 0. So let me just ignore them, and P plus Q is 1 because these events are complementary. Now, how to compute P and Q? So the question is how to compute them. And here is a solution which uses Craftsman formula. It goes as follows. Suppose we are looking at Q. So Q is the probability that the convex hull of the points contains 0. What is a convex hull? So it is the probability that there exists lambda 1, lambda n greater than 0, with which sum up to 1, such that lambda 1 z1 plus and so on lambda n zn is 0. This is just the definition of the convex hull. But now we can do the following thing. We don't like this condition that they sum up to 0. Suppose I have found such lambdas which do not sum up to 0, sum up to 1. Then I can just define by their sum, and then after that they sum up to 1. The only thing, or the only case where this is not possible is when all lambdas are 0. So if all lambdas are 0, then of course I cannot divide by the sum. But if some of them is positive, strictly positive, then I can divide by the sum, and this condition is fulfilled. So we can write it as follows. It is the probability that there are lambdas, lambda 1, lambda n greater or equal to 0, not all of them 0, such that lambda 1 z1 plus and so on plus lambda n zn is 0. Just rewritten the same thing. Now the vector of these lambdas can be denoted by lambda, so just an n-dimensional vector, and it is then in the orthant, but not 0. And now we can write this as the probability that there exists lambda from the orthant, but not 0, such that a lambda is equal to 0, where A is a matrix whose columns are the numbers z1, z2, and so on, zn. So it is a matrix which has n columns and d rows. So it can be considered as a linear operator from Rn to Rd. And why is this true? Well, because if A lambda is equal to 0, suppose I take this A and I multiply it by a column lambda, then this is 0 exactly if the combination of the columns with coefficients lambda I is 0. So it's just the same condition written in terms of matrices. And this means that lambda is in the kernel of A. And what is kernel of A? Kernel of A is a linear subspace, first of all, in Rn, and it has dimension. Well, the dimension is maximal here. It is n minus d, because the rank of this matrix is full. it is full because if I take here any d columns, then they are linearly independent with probability 1. What are columns? These are just points on the unit sphere. So if I take d points on the unit sphere at random, uniformly, then they are linearly independent with probability 1, which means that any d columns are linearly independent with probability 1, and the rank is d. It is maximal, and this means that the kernel of A has minimal possible dimension n minus d. So it's n minus, it's what one has if for a generic matrix. And also, so it is a linear subspace of dimension n minus d, but we also claim that it is uniform. Kernel of A is uniformly distributed. Well, what does it mean, uniformly distributed? It means that if I take this kernel and apply to it any orthogonal rotation, so any orthogonal matrix in Rn, then the resulting new subspace is going to have the same distribution. And this is the case here. Well, okay, maybe it's not so easy to see for the uniform points, but it's clear that nothing changes. So all this problem remains the same if I take them to be Gaussian on Rn, on Rd. Nothing changes. And then we have here a Gaussian matrix, just a matrix whose entries are IID Gaussian random variables. And it is easy to check that such a Gaussian matrix remains Gaussian if we multiply it by an orthogonal transformation from the left, say. And this means that the kernel is uniformly distributed. So it is invariant, and as such, it must be uniformly distributed. So what we have here is the probability that this orthant is intersected by the kernel of A non-trivially. So it is the probability that the kernel of A intersects the orthant non-trivially, not at zero, not just at zero. So we have the orthant, we have the orthant, and we have a subspace, and we want a non-trivial intersection. And now, by definition, this is a Grassmann angle with index d, because we have here codimension d. So it is Grassmann angle with index d of Rn plus. And now the Crofton formula tells us that this is 2 times nu d plus 1 of the orthant plus nu d plus 3 of the orthant plus and so on. And we computed the intrinsic conic intrinsic volumes, and the result is then 2 divided by 2 to the power n, and then we have a sum of binomial coefficients. So this is the resulting probability. It is 2 divided by 2 to the power n times such a sum of coefficients. It is q, and p is then 1 minus that. Now the second question, which is closely related, and which will also show us that what I stated here is just a very special case of Wendel's result. In fact, it is much more general, as I will try to explain now. So the second question was answered by Schläfli in the year 1850. It's a very natural question. Suppose we have in Rd, in a d-dimensional space, we have n hyperplanes and hyperplanes passing through the origin. Through 0. And the question is, in how many parts these hyperplanes divide our space? Now, the answer depends, of course, on the hyperplanes, but what Schläfli assumed is that they are in general position. So assume hyperplanes are in general position, which means that every d normal vectors to these hyperplanes, so I can call these hyperplanes, say HU1, HUN, U1, UN are the unit normal vectors, and this means the general position means that every D normal vectors U1 among U1, UN, so there are more than D. We have here n greater than D, by the way. So there are more than D vectors, but if I choose any D, they should be linearly independent. Are linearly independent. So maybe I have to say among U1, UN. And now the question is the number of paths in which these hyperplanes split the space. Now we shall see that this question is equivalent to the question of Wendel in some sense. So more or less it is the same question. Maybe it's not immediate, but it is the same question, essentially. So the hyperplanes generate half spaces. And let me look at the half space H U1 minus intersected H UN minus. So every half plane generates two, every hyperplane generates two half spaces, plus and minus. And we can combine them, so we get 2 to the power n combinations. But not every such combination is non-empty. And our question is to count the number of non-empty intersections, right? So let me consider just one example of such an intersection where I take all the signs to the minus, and we want to consider the case where it is non-trivial. So it is not zero, not zero. What does it mean? This means that there is X in RD without zero, such that all unit vectors Ui scalar product with X are smaller than zero for every I. Just by definition of HU minus. So there is a vector which has negative scalar products to all of the vectors Ui. Now, under which conditions is this possible? So suppose we have here U1, U2, U3. Let me consider the positive hull of them. This is the positive hull. If this is the positive hull, can I find such a vector X which has negative scalar products? Yes, it is somewhere here. This would be X. And under which condition it is not possible to find such an X? Well, the only case is if the positive hull is equal to the whole of RD. Because if it is not RD, if it is non-trivial subcone there, then there is always such vector X. I'm not showing it, but I think it should be intuitive. So actually the set of all such vector X is called the dual cone. And the dual cone is non-trivial if the cone we started with is not RD. So the condition can be written as the condition that the positive hull of U1 of these vectors U1 UN is not RD. It is the same condition. Or if we now argue in the same way as before, now we have the same situation as before, right? We want that the positive hull is not RD, and it is the same, exactly the same question we had before, because the convex hull contains zero if and only if the hull contains zero in the interior if and only if the positive hull is RD. So we have here, as in question 1, we can write it as the event that the kernel of A intersects the positive orthant plus trivially. So this intersection of half spaces is non-trivial even only if the kernel of A intersects the orthant trivially. And A is again a matrix whose columns are U1, UN. So A is a matrix with columns U1, un here. But now we have not just this intersection of half spaces, we have 2 to the power n intersections where we can change the signs. So if we have an intersection of the form HA1, U1, H epsilon n un, where epsilon I are signs, plus minus ones, then this intersection is non-trivial if and only if the kernel of A does not intersect the orthant. And now it is not the basic orthant I defined below, but it is the orthant R epsilon 1, R epsilon n, where R plus is the positive half line and R minus is the negative half line. So we have in the space Rn, we have this orthant, which is where all coordinates are positive, but there are 2 to the power n similar orthants, right? Where the signs of, for each such orthant, the signs of the coordinates are fixed, is defined by fixing the signs of the coordinates. And now such an intersection is non-empty or non-trivial if and only if the kernel of A doesn't intersect the corresponding orthant there. So what we now want to do in this Schläfli question is to compute the number of orthants among the 2 to the power n orthants. We want to compute the number of orthants not intersected by kernel A. So our question is compute the number of orthants not intersected by the kernel of A. So we have orthants 2 to the power n, and we have a subspace kernel A, random, not random. In this example, it is not random, and it has dimension n minus d because of the general position assumption. And we want to compute the number of orthants not intersected by it. Now, a claim which I cannot prove in the remaining 2 minutes is that actually this number does not depend on the kernel of A as long as it is in general position. So under this general position assumption, the number does not depend on the choice of the subspace. So for example, here we see that it's not important which line I choose, as long as this line is not a coordinate line. As long as it is not a coordinate axis, the number of orthants intersected is always 2. And this is the case in the n-dimensional space. So what I could do, I could replace a non-random kernel, non-random subspace, which is here in this Schläfli question, it is non-random. I could replace it just by random and take the expectation, right? And it would be the same. So the expected number of orthants not intersected is the same as the number of orthants not intersected, because the random variable of which I take the expectation, namely this number, is constant. So we can just use the previous result, and we see that this number, it is just 2 to the power n, which is the number of all orthants, times the probability that one orthant is not intersected. And it was denoted, as far as I remember, by p. So if we simplify it, we get 2 times the binomial coefficients. Well, in Q, we had binomial coefficients increasing with increasing indices, and here we have decreasing indices, plus and so on. And this is the number of parts we wanted to compute. Now, I think I have, at some point I have to stop, but maybe I can mention that from these considerations, we see that the question of Wendel was answered, or the result we proved here was not the most general one. So here we have taken Gaussian random variables, and the subspace they generated was to have a uniform subspace. What is here really important is that each orthant is intersected with the same probability. And the result of Wendell would be true. So actually true under a much weaker assumption, namely that Z1, Zn are arbitrary, maybe even dependent vectors in Rd, such that the law of plus minus Z1, plus minus Z2, and so on, plus minus Zn for arbitrary signs is the same as the law of Z1, Zn. This guarantees that all orphans are intersected with the same probability, and then the above reasoning can be applied. So if we just impose the assumption of such a symmetric invariance under sign changes, then we can still prove the result of Wendell and some general position assumption. Okay, now I think I have to stop at some point, and actually it was clear from the very beginning that it would be not possible, but my goal was to explain the analogues of these results. Oh, I have done something very, very bad. Sorry. In the case in which the group of random sign changes is replaced by the symmetry group and the orphan is replaced by a Weyl chamber. In that case, we get results on the probabilities that random walks or convex house of random walks do not absorb the origin. But I think I have to stop here. But I have to try to, yeah, okay, so I think it's okay now. Yes. I think we can stop here. Maybe just a short question to you if I have time. I can ask the question, otherwise, so it's a question to you. You can think about it. So suppose we have in Rd, where D is very large. So D is 1 million. And in this Rd, we choose endpoints uniformly at random on the sphere. And so we choose, say, first 1 point, then 2 points, then 3 points. And at some, if the number of points n increases, then at some moment of time, the convex hull of these points will absorb 0. So if the number of points is sufficiently large, if this n is sufficiently large, then it is clear that this convex hull at some point should absorb the 0. The question is how large this n should approximately be in order to have such a absorption. So how large should be n approximately in order to guarantee that the probability of absorption is 1 or close to 1. So how large should be n so that, or to guarantee that the convex hull of these points contains 0. Okay, let me stop at this point.
Okay. Thank you, Zakhar. Thanks for a wonderful talk. So first, all the participants will be now unmuted, so we can give a round of applause for Zakhar. Unmute yourself. You'll be given the option now. And all of you, anybody who wants to ask a question, you can unmute yourself and ask the question. I think now you'll be, it's allowed. Or you can post a question on the chat.
Yogesh, this is Parthanil. Can I ask a question?
Yeah. Please go ahead.
It's sort of little unrelated, but just since the last question is posed. So Zakhar, if one wants to simulate a uniform random variable in a d-dimensional sphere, how expensive is the algorithm? Do you know anything about that? It's just a completely unrelated question for us.
I would do the following. I will simulate Gaussian random variables xi1, xin, which has linear time.
Right.
So we need linear time to do that because the simulation of one Gaussian random variable is just Box-Mahler algorithm standard.
Right.
And then we take xi1, xin, and divided by the norm.
Okay. Okay.
And this is uniform.
Rotational symmetry, essentially.
Yes, it is rotational symmetric, and there is just a unique rotational symmetric.
So this is linear, essentially. Okay.
So it's linear.
Thank you. Thank you, Zakhar. Yeah.